All right. Share my screen. Can anyone see my screen?
We got it.
Yes.
Awesome. Thank you. Thank you, David. And thank you all organizers for opportunity to showcase our technology today. So again, my name is Hojun Lim and I'm from Sandia National Labs. And in this presentation, I'll be talking about our material data-driven design, or MADCube that we call it. All right, so our technology is aimed at revolutionizing the manufacturing process by utilizing the power of machine learning. Obviously, as Abby mentioned, AI and machine learning are the emerging technologies that eliminates iterative, time-consuming, and resource-heavy procedures in industry. And our software, MADCube, uses this machine learning framework to obtain materials' mechanical properties without performing physical experiments of metallic materials. So, this technology will hopefully bring new paradigm in industry, manufacturing, and innovate many engineering applications. So here's our team, myself and David Montes de Ocazapian. We are both computational materials and data scientists here at Sandia. And we teamed up to take our theoretical models and computer codes outside our lab and hopefully have a broader impact. So we developed this technology about a year ago. We published a couple of peer-reviewed journal papers and got a lot of traction inside the lab, but we really needed to go outside and talk to people, especially in industry, to get to know their needs and the current market. So last year, we were fortunate enough to be funded through DOE's ICORS program, and we did some customer discovery and really start to think about commercialization of our lab developed technology. So we talked about 120 people, engineers in industry, scientists in national labs, professors in academia, and just to really understand this field. We had meetings with the major auto companies like Ford, Toyota, GM, some of the metal suppliers like ArcelorMittal, Novelis, and some software companies like PamStamp, Simulia, and Autoform. And then from these interviews, we were able to nail down like 3 major issues they had. They really needed to know materials' mechanical properties quickly and accurately, but the current practice is time-consuming, it is expensive, and it is reactive rather than proactive. For example, even like major auto companies in the US did not have a right equipment to measure directional mechanical response. So a lot of times they had to rely on old materials database or outsource the experiments to academia or other specialized lab, even outside the country. And then the other issue they had was the complexity in R&D data. These data are usually complicated, pretty large in size, and it's very difficult to implement into actual manufacturing processes. And then one of the NASA employees said, unfortunately, you can have PhDs in every step of the line production. And you can't build that spaceship with all the PhDs in the line. So, there's definitely a staffing issue. And then this is worse for automotives and metal companies. And then there's another issue with the environment and carbon footprint, because a conventional method requires a lot of mechanical testing, a lot of materials. So, that has an issue in this carbon footprint, which we care about a lot. And so this is our solution, a machine learning-based software that instantly predicts materials' physical properties. This is all virtual. Obviously, it saves money for companies. They do a lot. They could save a lot in their experiments, less materials, reduced staffing costs, and it is fast. It is about 1,000 times faster. It is actually a fraction of a second compared to doing some physical experiments, which usually takes a few months in their own labs, or get the data back from their external collaborators. And again, this technology is all virtual, so you could alleviate these carbon footprints. The other interesting thing I just want to bring out is that this technology could transform operations. One of the things that we noticed very quickly is that there was a big gap between R&D side of the company and then the manufacturing side of the company. So we are trying to come up with a very easy to use software solution, which we hope that it will bridge the gap between these two sectors. All right, so I'm going to talk about our technology in more detail in this slide. So if you take a look at the right-hand side, this is the backbone, the theory of our software. It is machine learning-based model, and it is trained from Sandia's high-fidelity simulation using high-performance computing. So we generated huge data set, computational data set. We actually ran like 54,000 scenarios of different materials, and we trained the machine learning code based on that huge data. So our input is material's internal structure. So if you know the material's internal structure from microscopes or X-ray, this machine learning code will instantly give you material's directional mechanical response. So all this work, theory, math, framework, and validation with the actual experiments is all documented in this paper that I listed there in Material Science and Engineering A. It's recently published. So this code was great, we liked it, it's useful, but we really needed to package it into a standalone code so that people can actually use. So the left-hand side, the screen is the actual graphic user interface of our software, the current version. So it is all packaged into a standalone code in both Mac and Windows operating systems. So you're basically a few clicks away. You just input your material information, and it spits out that material directional mechanical properties. And then now this software is protected by DOE software copyright assertion. And I just want to mention that I think we have a pretty high TRL level, a level of 6, which is defined as a representative of the deliverables demonstrated in relevant environment. And I think the current form of our software really fits that description. So again, our philosophy was to come up with a very easy to use. Anyone who does not have a machine learning background or Ph.D. in material science can use it. So once you have all that data, the actual engineer can use that information, plug it into their analysis tool, like finite element software that they use, and they can really forecast or predict materials behavior. On the right bottom, you see actual application using the information from the math cube. This is a cup drawing, and you can kind of see how it could be applied in metal forming analysis. So we actually had a chance to showcase our technology to many research groups, and we got really positive feedback. Just a couple of quotes I just presenting here. Especially in Ford, they really liked the technology. They really wanted to apply it in their production line and see how it goes. And Novelis, one of the biggest aluminum company, they liked the fact that you can bypass all the physical experiment and get these material properties very quickly. So we were very motivated with these interviews. And then based on our internal research and discussion with the Sandia's business and competitive intelligence team, we see the total addressed market of $1 billion that we can impact. And this is the size of all commercial software companies, software market. And from this total market, we see about $200 million market growth opportunity. And that's the size where people are directly using material information in their analysis. So this includes like a metal stamping, material qualification, forming analysis in like automotives or metal suppliers. And then also based on our market analysis and initial discussions with the actual die designers, material characterization engineers, and we kind of anticipate $50 million initial market entry point. From their direct feedback and discussion, I think this looks very attainable and promising. Right. So I think we are very competitive, especially if we place our software in this accuracy versus speed plot. So obviously you want to be on this top right corner, you want to be fast and accurate. And this code satisfies both speed and accuracy. So if the conventional method, like commercially available simulations, you lose a lot of accuracy. Or if you want some accuracy, you need to do some high fidelity simulations or physical experiments, and you lose a lot of speed, which means it costs more. So we're very excited about this new paradigm using machine learning in the actual manufacturing. So my last slide is the blueprint of our roadmap. So since 2018, we had this steady ongoing R&D funding from Sandia that will continue for a few more years, that will keep us up to date with the technology. And then, like I mentioned, last year, 2021, we received this Energy I-Corp funding to really start thinking about the commercialization, customer discovery, and align our technology to that direction. We recently asked for STM funding, Sandia Technology Maturation Program, which I think will push us to that final stage of the product and help us get to that final goal in 2024, where we can have we can deploy the product and be ready for the prime time. All right. With that, I'd be happy to answer any technical questions, or feel free to reach out to me or David. Emails are there. Or for more licensing questions or more business side of the questions, I'm gonna ask you to contact ip@sandia.gov. We are getting a lot of momentum in this work. Our work was recently featured in lab news and few social media posts. So we really hope that this technology will have a broader impact outside Sandia. Right. Thank you very much and appreciate your attention. Thanks.
Great, thank you, Dr. Lim. With that, I will hand it over to the Sharks.
So once you get this out into the marketplace, what do you see is your business model?
Right, that is a great question, and we are still talking with tech transfer office folks and legal offices and etc. So, but what we are currently doing for the next couple of years will be incorporating early adopter suggestions and how this can be improved. So that will be our main focus. And once we have all that features and things that people want, I think that's where we are going to start thinking about how this can be, deployed. I think we have a few options. There could be a spin-offs, or we could, everything is developed on the Sandia lab. So there's a lot of complexity there as well.
So the last question is, when do you get this to a potential customer where they can actually use it, maybe do some sponsored research for you all? At what point in time is that? Is it this year, next year, the year after?
Yeah, the current version is actually circulated within Sandia to early adopters. And so the technology itself is pretty much ready. But we will probably need some feedback from industrial partners. And that's why we asked for that STM funding for next maybe year or two to really become a useful software or app for the industrial partners. So I think we need another year or two to really sell and make a useful for the industry partners.
I have a question. I understand you are using an alloy and certain data describing this alloy, combine it with your algorithms in order to predict certain mechanical properties. Can you also turn it around in order to satisfy certain boundary conditions in terms of mechanical properties? What could potential alloy candidates be in order to actually optimize the alloys for specific usage?
Right, that is a great point. That is a great question. Actually, we thought of, so the current software does not do that. So we have to go the other way. It needs to be inverse problem that we had. So our current program won't do that, but that was some research idea David and I had, and we submitted for our LDRD last year. So that's some area that we really want to know, that material optimization based on like a final, like a property that we need. I think that's something we're heading towards to using machine learning algorithm.
All right, any last questions from our sharks?
Just one more. So machine learning platforms typically need a lot of data to learn. So in that context, maybe I don't fully understand, how you achieve the accuracy without the physical experimentation, but how do you make it smarter over time?
I'm sorry, how
do you make it smarter, better over time? Do you depend on the feedback from your commercial customers, or how does it work?
Yeah, that's a good question. So our machine learning is as good as that training data that we have. And that training data is from high fidelity simulation, which is pretty accurate. I can maybe send you a paper that shows how it compares with actual physical experiments. It's within some experimental tolerance. But again, if you have some special materials with complex crystal structures, for example, we'll need to add in that physics into our high fidelity simulation training data. And also, if we have more experimental data, different materials, we can always train our data machine learning. And I think that's the beauty of the machine learning. If you have more data, you can train it. You'll probably interpolate or extrapolate a little bit better. So that's definitely one of the areas we are trying to improve.
All right. Well, thank you, Dr. Lim. Thank you to our sharks for these great questions. Our final presentation this morning for this panel is Engineered Carbons for Biomedical Applications with Dr. Nikolai Hojun.